Welcome to The Explainer. Today, we're going to decode the secret language of the universe. I'm talking about the mathematical recipes that describe, well, pretty much everything, from a falling apple all the way to a rising stock market.
I mean, think about it. From a cup of coffee cooling on your desk to the orbit of a planet, our world is just constantly in flux, right? So how in the world do we write the recipe for that? Well, today we're diving headfirst into the mathematical language that describes change itself.
And that language? It's the language of differential equations. Yeah, I know, it sounds a bit intimidating, but stick with me. These are the incredible tools that scientists, engineers, you name it, they use them to stop just observing the world and actually start predicting its future. So let's get right to it. If you strip away all the fancy jargon, what exactly is a differential equation?
Okay, so at its absolute core, a differential equation is really just a rule. It's a rule that describes a rate of change. You know, if you ever see an equation with a term like dy over dx, which, by the way, is just a fancy way of asking how fast is y changing whenever x changes, then yep, you're looking at one. It's basically a recipe for how something evolves from one moment to the very next. But here's the thing, not all change is created equal, right? And that's why every single differential equation has these two key identifiers, think of them like a fingerprint, that tell us exactly what kind of change it's describing. So let's decode them.
First up is the order. This one tells us about the complexity of the change. So, for example, a first-order equation might be talking about an object's velocity, its rate of change of position. But what if you need to bring acceleration into the mix? Well, acceleration is the rate of change of velocity, so now you're going to need a second-order equation. See how that works?
Okay, so once you've spotted that highest order derivative, the degree is just its power, its exponent. Super simple. If that term is squared, the degree is true. If it's cubed, the degree is 3. Easy, right? Well, there's a catch. And this is a big one. There's this one critical rule for finding the degree, and it's that the degree can only be determined if the equation is a, quote, polynomial in its derivatives. So what on earth does that mean in practice? Well, it means that for the degree to even be defined, all the derivative terms have to be free. They can't be trapped inside other functions like sine or log, or stuck under a square root. It's like they have to be standing out in the open. If you can't use algebra to free them up, to get them standing on their own, then the degree is just considered not defined. And that rule? It's absolutely crucial for understanding the basic structure of the equation.
All right, let's switch gears a bit. The relationship between an equation and its solution, it's this really fascinating two-way street. We're not just hunting for a single lonely answer here.
You see, solving a differential equation is, well, it's kind of unique. It doesn't just give you one answer. No, it gives you an entire family of curves. Let's go back to that cup of coffee. The equation doesn't just describe how your cup of coffee cools, it describes how any cup of coffee cools. So that family of curves is literally all the possible ways it could cool down, whether you started with it boiling hot or just, pleasantly warm. And this is what illustrates that duality so perfectly. On one hand, you can actually start with a bunch of solutions, say a whole family of circles, and work backward to find the one single differential equation that governs all of them. But then, on the flip side, you can start with just that one rule, that one equation, and work forward to discover the entire family of curves it describes. It's two sides of the same coin.
Okay, so that's the theory. But how do we actually go from the theory to the reality? Let's take a quick look at one of the most intuitive ways to solve these things.
One of the most common techniques is called variable separable. And honestly, it's pretty much exactly what it sounds like. You just use some algebra to sort the variables. Get everything with a y on one side of the equation and everything with an x on the other. Once they're all separated out, you just integrate both sides and boom, just like that, the whole family of solutions appears. So, we've decoded the language, we've seen a little bit of how it works, but let's get to the big question. Why does all of this abstract math matter so much in the real world? It's because these equations are the code of the universe. Seriously. They're the recipes that govern these incredibly complex systems all around us. We're talking about everything from the physics of a swinging pendulum to the design of an electrical circuit, all the way to the finances of the stock market. Differential equations provide the fundamental rules of change. And that right there is the true power of all this. It's what allows us to move from just observing change to actually accurately predicting it.
They transform us from passive observers into active predictors. They give us a real framework for asking what if and getting a solid, mathematically sound answer back. So here's a thought to leave you with. If a single, simple equation can describe an entire family of possibilities, what does that say about the hidden rules that are governing our world? It kind of suggests that beneath all the chaos we see, there are these elegant, hidden rules of change just waiting to be discovered. So the next time you see something in motion, anything at all, just remember, you're probably watching a differential equation tell its story.